Hello and welcome to CO 738 Probabilistic Methods. Today we'll be discussing linearity of expectation. So what is linearity of expectation? Well, if x is a discrete real random variable, we remind you that the expectation of x, denoted e of x, is equal to the sum over I, where I is in the support, of I times the probability of x equals I. In normal parlance, this would be called average or mean, but here we refer to it as the expectation. Then what is linearity of expectation? Well, the linearity of expectation says that if x is the weighted sum of discrete real valued random variables, so x1 up to xn, and again weighted, so here we have c1 times x1 plus c2 times x2 up to cn times xn. So if x is this sum, then the expectation of x is also the weighted sum of the expectations, namely the sum over the i's of the ci times the expectation of xi. Thus, expectation is acted upon linearly when doing addition. Thus, linearity of expectation. And note again that this holds even if the xi are not independent. So it has nothing to do with independence. Rather, again, this works always. And we will often use the facts that there exists a point in the probability space, an x, such that x is therefore at least the expectation of x. And there's also a point, maybe a different point, where x is at most the expectation of x. So we will be using these facts. We will set up an appropriate variable, calculate its expectation using linearity, and say, there exists a point that's at most or at least the expectation. For an outline today, we will be doing a number of examples using the linearity of expectation. We will study the following. There will be Hamiltonian paths in tournaments, large bipartite subgraphs, balancing vectors, and unbalancing lights. So again, the focus of this course is on the methods that we will show via numerous examples. Let's start with Hamiltonian paths in tournaments. Recall that a tournament is an orientation of the complete graph, viewed as one player beating another in a tournament and thus having the direction. A Hamiltonian path in a tournament T is a directed path that includes all the vertices of the tournament T. So a Hamiltonian path in a graph is just a normal path, an undirected path that includes all the vertices. Here we will need it to be directed from one end to the other, so that all the edges have the same direction. A natural question is, what is the maximum number of Hamiltonian paths in a tournament with n players? So how can we maximize the number of these Hamiltonian paths? And a nice result in that regard is the theorem by Sella from 1943 that there exists a tournament T with n players and at least n factorial times 2 to the negative n minus 1 Hamiltonian paths, which is indeed quite a lot. And a note on this is, again, it's arguably one of the first uses of the probabilistic method, predating Ehrlich's 1947 result. Also, Alon in 1990 showed that there are at most n factorial over 2 minus little o of 1 to the nth Hamiltonian path. So this is nearly tight, that we know it's at least n factorial over roughly 2 to the n, and at most, at least the base of the exponent there is of the correct order. So that is the result. We will move on with the proof. So what shall we do? Well, we're going to take a random tournament, T, where each edge is oriented independently equal in either direction, just as we did when dealing with tournaments before. So that's our probability space. Now we need to calculate a variable whose expectation we will calculate. So let's define this variable. Let x be the number of Hamiltonian paths in T, as is natural, the thing we are interested in. So let x be this number. How will we calculate its expectation? Well, let's view it as a sum. To that end, for every permutation sigma of n, we'll let x sigma be the indicator random variable for whether sigma 1, sigma 2 up to sigma n is a Hamiltonian path, that this vertices in that order form this Hamiltonian path. That is, there's an edge from sigma 1 to sigma 2, from sigma 2 to sigma 3, up to sigma n minus 1 to sigma n. So this is a possible path. What is it? Again, an indicator random variable, if you're unfamiliar with probability, is the variable which assigns 1 if the event happens and 0 otherwise. So this would be 1 if it is a path and 0 otherwise. Thus, it's clear that x is actually the sum of these indicator random variables, 1 or 0 for each potential Hamiltonian path. So by linearity of expectation, the expectation of x is the sum over these permutations of the expectation of the x sigmas. What's the expectation of x sigma? Well, it's an indicator random variable. It's 0 if it doesn't happen, 1 if it does. So it's exactly equal to the probability that this sigma forms a Hamiltonian path. What is that? It's 1/2 to the n minus 1. For each edge, there's a probability of 1/2 goes in the right direction. There's n minus 1 edges in the path, so the probability is 1/2 to the n minus 1. Thus, it's the same for every x sigma, so we can instead times by the number of terms instead of taking a sum. What is the number of terms? It's the size of Sn, the number of permutations, which is n factorial. Thus, we get the expectation of x is equal to n factorial times 2 to the negative n minus 1. Thus, with our last observation that there must exist a point in the probability space, at least the expectation, there exists a t, i.e. a tournament, that has at least n factorial times 2 to the negative n minus 1 Hamiltonian paths, concluding the proof. So again, a nice short proof where we just calculated an expectation and then said there's at least a tournament with that many paths. Let's move on to our next example about large bipartite subgraphs. So a natural question to ask in graphs is, does there exist a bipartite subgraph of a graph with many edges? So that's very large, and here many edges is a way to say that. And a nice theorem is that every graph G has a bipartite subgraph with at least half the edges, so at least E of G over 2 edges. So you might want to stop and pause the video and prove this to yourself. There's actually a nice non-probabilistic proof, and we'll discuss that a bit, but there's also a very short, nice probabilistic proof. So that's what we will be doing first. So let's go ahead with that. How are we going to use randomness here? Maybe stop and think. So what's the randomness? What's the proof idea? It is to take a random bipartition of V of G. So we want a bipartite subgraph with the two parts, so we will take a random bipartition. What is that equivalent to? Well, let T be a random subset of V of G, where each vertex is in T independently with probability 1/2. Clearly the same as a random bipartition, so here T will be one part and V of G minus T the other. Then, what would our subgraph H be? It would be the graph with the vertices of H being the vertices of G, and the edges of H being the crossing edges. That is, the edges equal x, y, where x is in T and y is in V of G minus T. So one end in one part, one end in the other. Then clearly, H is a bipartite subgraph of G. It's a subgraph, as we're just maybe deleting edges, and it is bipartite, given the definition. Thus, we have H. Now we can move forward with calculating our expectation. To that end, we need a variable. Clearly, the variable should be the number of edges of H. So to that end, let's calculate first the probability that a given edge is in H, or E of H. And I claim that that probability is 1/2. So we might want to pause and think about why this is true. But here's the answer. It is that, what is the probability? Half is a quarter plus a quarter. So there's a quarter chance if E is xy, that x is in T and that y is not. And then there's a quarter chance of the reverse, that y is in T and x is not. And those sum together give you a half. Given that, we can now use linearity of expectation to say the expected number of edges of H is the sum of the indicator random variables for each edge, whose expectation will therefore be the probability of E and H, which we've already determined from above is 1/2. So the sum of the edges being 1/2, it's the same for every term, so we extrapolate by the number of terms, which is the number of edges of G, so we get 1/2 of E of G. For the expected number of E of H, so there exists an H as desired, because again there'd have to be an H where E of H is at least the expectation, which is 1/2 of E of G. And that concludes the proof. So again, another short, nice proof. We set up a random process, we took a variable and took its expectation and said there's a point here with at least that amount, just as we did with tournaments. This one is nice though because it admits de-randomization. So it can be de-randomized by doing the following. You might want to pause and think through how you would de-randomize this. So to take out the randomness, it leads to a nice non-random algorithm. So what's the idea is we put the vertices in the parts sequentially. So we put them in either T or V of G minus T sequentially. So instead of doing all of the coin flips at the beginning at once, we instead look at each choice and do it in sequence. Then how do we make the choice? Again, we want to maximize or minimize, depending on what we're doing, the variable we're interested in. So here it's the number of edges in H. We want to maximize that. So at each stage, we choose the choice, t or v of g minus t, such that at least half of its previous neighbors of the vertex are in the opposite side, guaranteeing at least half of its edges are going into H. So this is the way to de-randomize it, where we make the choice as we go. So very nice. That's a non-random proof and also nice algorithm that covers this proof. So that's it for the bipartite subgraphs. I will mention, though, that you can actually use the same de-randomizing idea to do pairs of vertices as well. So you could take somehow pairs of vertices and put them each on a different side, but do that according to which way maximizes the edges. And same with the randomness proof. So I won't go into that, but it's actually possible to get this bipartite subgraph to have the number of vertices be equal on both sides. So think of that as an exercise. We'll now move on to a harder example, which is about balancing vectors. It comes from the following natural question. Given a collection of unit vectors, can we add or subtract them so as to be close or far from the origin? So suppose we have unit vectors, which you can think of as directions, and each time we're presented with a direction, we have to either go in that direction a unit distance or go in the opposite direction. Then is it possible to get back to when we end up close to where we started, to this origin? Or vice versa, can we ensure that we end up at least a bit away from the origin? And the answer is yes, as per the following theorem. Let v1 up to vn be unit vectors in Rn. So here we're using Euclidean norm, I'll denote with bars. So the Euclidean norm would be 1. Then the claim is that there exists epsilon 1 up to epsilon n in minus 1 plus 1. So if you take this weighted sum, then you take the norms, that would be the distance, is at most the square root of n. So you can end up within the square root of n distance of the origin, and vice versa, there exists epsilon up to epsilon, maybe same, maybe different, where the weighted distance there is also at least the square root of n. So we have this dichotomy. Yes, we can end up close to or far from where that number is the square root of n. So why square root of n? Well, we'll look at that, but this seems somewhat reasonable considering the maximum distance could be as much as n if you kept going in the same direction, they say, if all of the v's were the same. So square root of n seems like a nice compromise. All right, so that's our theorem. Now here's our proof idea, is to choose the epsilon I randomly and use expectation. Right, so we have these choices. Let's just make all the choices randomly and independently and use expectation and argue that the expected value is somewhere around square root of n. So let's proceed with the proof. So let epsilon n up to epsilon n be chosen independently and uniformly. So each plus or minus 1 with probability a half. Then we'll let x be, instead of looking at the norm, we'll actually look at the norm squared, so the square of the distance. Why is that? Well, it's going to be easier to work with, easier to analyze. Because when we square this norm, it ends up being equal to the sum of I over the sum of j of epsilon I, epsilon j, vi, dot product with vj there. So the dot there is the dot product. So that just works by expanding out this dot product. So that is our x, that's our variable we're looking at the square. Now we will use linearity of expectation to argue that the expectation of x is the sum over I, sum over j, of the expectation of this epsilon I, epsilon j, vi dot vj. But vi dot vj, those v's are fixed vectors, so their dot products is just some fixed constant, and thus we can actually take the expectation just on epsilon I, epsilon j. So you may want to pause the video and think for yourself, what is the expectation of this epsilon I, epsilon j? We'll now proceed with the answer. So when I is not equal to j, then epsilon I and epsilon j are independent, and thus the expectation of their product is simply the product of their expectations. This only works when they're independent. Then the expectation of epsilon I is, of course, 0, as is j, so 0 times 0 is 0. Why is that? Well, with half, probability half, it's minus 1, probability half, it's plus 1, those cancel out, the expectations are 0. So that's when I is not equal to j, all those terms disappear. They get canceled out and go away. Now, what happens when I equals j? Well, then epsilon I and epsilon j are the same, so we get epsilon I squared, and that expectation is just 1, since if epsilon I is plus 1, 1 squared is 1, and if it's minus 1, it's also 1. So either way, it's 1, and thus the expectation is 1. Thus, all that are left in our expectation of x are these terms where I and j are the same, in which case epsilon I squared is 1, and vi dot vj, well, if j is I, then you get vi dot vi, which is vi squared. Since it's a unit vector, that becomes 1, so we get the sum of n1s, which is just n. So the expectation of x is n, and now that means that there exists a choice of the epsilon I, such that x is at most n, and similarly a different choice where x is at least n. So there's always an outcome in this probability space, which is at most and at least the expectation. If we take that choice, then of course, when that choice gives us that the square root of x, the original distance, is at most the square root of n, or at least the square root of n as desired, ending the proof. So that's our proof. We just chose the epsilons independently and randomly and calculated the expectation. The only interesting part here was that we used the square, as you can see, to simplify our calculations. I will point out there's also a nice generalization of this result, which goes as follows. Let v1 up to vn be vectors in Rn. Here they're not unit vectors, they're just at most norm 1. And let p1 up to pn be 0, 1, so that think of them as weights. Then we define w to be this kind of weighted sum of the v's. So p1 v1 plus p2 v2 plus up to pn vn. Then the claim is that there exists epsilon 1 up to epsilon n in 0 plus 1, so not minus 1 plus 1 anymore, but just 0 plus 1, such that w minus v, the norm, is at most the square root of n over 2, where v is epsilon 1 v1 up to epsilon n vn. So what is this and how should you think of it? Well, now what we have is we have a collection of vectors and we have a weighted sum of those. So w is somehow a weighted sum of these vectors. It's where we've got to. Then the idea is that actually, no matter what, we can always just take the vector 0 or 1. So for each vector, we can either leave it out entirely or take it. So in some way, it's somewhat of an integral rounding of w. That will be v, in such a way that it's approximately the same. So that v is still quite close to w. So that's somehow nice that if you can get from, point A to point B via these various steps with weights, then actually you can get there in a somewhat more integral fashion with only integral steps for the vectors. So that's the idea of the theorem, this generalization. Why do I say it's a generalization? Because if you put in p1 to pn being a half, then you would find that w is just kind of the sum of all the vectors but divided by 2, and then it implies the case as before, up to a small translation. So then if you shifted it from 0, 1 being the things to minus 1 and 1 and timesing by 2, you'll end up with the theorem as before. So our old theorem was a special case of this theorem. This is a bit more general. What's the proof idea is similar. So you choose the epsilon i's independently, but here, instead of half and half, you should do it according to the pi, the weight. So namely, the probability that epsilon I should be 1 should be pi, and the probability that epsilon I should be 0 should be 1 minus pi. And then you would just let x be this w minus v norm, except again squared. So we use the squared trick, and we can show in a similar fashion that the expectation of x is at most n over 4 as before. So here we get an over 4 because we'll get a pi times 1 minus pi, which will be upper bounded by a quarter if you do out the calculation. So I'll leave that as an exercise. I won't actually do this proof. And again, refer you to London Spencer if you want to see the details. But this it follows in a similar fashion, so I won't repeat it for you. But it's nice to know that this generalized theorem also holds. Then let me talk about de-randomizing. So can we de-randomize these two results? And the answer is yes. And the first one, the balance vector, has an especially nice interpretation. So let's go through that. How would you de-randomize? Take the randomness out of choosing those epsilons. So again, the idea is sequential, that we will sequentially choose the epsilon I to minimize or maximize the norm of these partial sums. Wi equals epsilon 1 v1 up to epsilon I vi. So think of making a series of steps, and each step, each vi, you can choose to go with it or backward. then I claim we can actually stay close to home, or far from home if that's what's desired. So let's go through the minimize case first. If minimizing, you would choose the epsilon I plus or minus 1, such that epsilon I vi, this latest step, makes an obtuse or right angle with wi minus 1. So i.e. that's wi minus 1, dot product with epsilon I vi is at most 0. So what's the intuition there is that we're at a certain point and we want to get back toward home, so we'll try to return home. We'll go at an obtuse or right angle. We'll go backwards. So that's the idea, and indeed, using induction, then you can show that wi squared, which of course is equal to wi minus 1 squared plus the epsilon vi squared, the new step, plus 2 times the dot product of wi minus 1 and epsilon I vi. Since that dot product is negative, that's at most wi minus 1 squared plus epsilon I vi squared. And by induction, you could show then that wi minus 1 squared is at most I minus 1. The new step has distance only 1, and together that would give you I, showing that wn squared is n, and thus rederiving the theorem. So this is particularly nice. As a narrative interpretation, we came from the random perspective, but we found a non-random proof by doing it in sequence. And it has a nice narrative in that if you want to stay close to home, you should try to go back. You should go back from, instead of the way you came. Instead of going onward, you turn around as best you can at each step. And then similarly, if you want to maximize, if you want to be far from home, you choose the epsilon I so that epsilon I vi makes an acute or right angle with wi minus 1, i.e. that they have positive, or non-negative rather, dot product. And then using induction, you get the same, but except you get a greater than equal, so greater than equal to I, so you'll end up further away from home. So again, a nice narrative interpretation that if you want to end up far from home, you should always head further in the direction that you're going as best possible, that head off toward the horizon. All right, so that's the de-randomizing of the balanced version. What about the unbalanced version? The weighted version we can do by de-randomizing. So we can de-randomize that similarly by choosing epsilon I to minimize the partial sums. So how does that work? So there, we at each stage have to choose whether it's 0 or 1, and we know, we did with coin flips, we had pi and 1 minus pi as the probabilities. We knew in expectation at each step that we were on making the sum small, and so at each step instead we just pick the option that we know will lead to minimizing the sums. So this ends up working because sums can be instead done sequentially, and so can be de-randomized as such. So that's our talk about de-randomization, some very nice examples from today. Here we did a bit harder one where we de-randomize sequentially. We won't always be doing this, and it doesn't always work, but it's nice to see it when it is in practice possible. For our last example, we will talk about unbalancing lights. So that first theorem of going far or close to home could either be viewed as balancing vectors or trying to unbalance them. Here we'll do something similar, but with matrices. How does this work? Well, let aij be plus or minus 1 for every ij in n. Then their claim is there exist xi yj plus or minus 1, such that the sum over I sum over j of aij xi yj is at least the square root of 2 over pi plus little o of 1 times n to the 3 halves. So that's quite a mouthful. How should you interpret it? The claim is, one way to think of it is you have a matrix, plus or minus 1 matrix A, and the claim is that there exist vectors x and y, so when you product, x, a, y is quite positive, is at least n to the 3 halves on the order of. Another more amusing interpretation of this is to think of that matrix rather as lights, so an n by n array of lights. And then each light is either on when aij is 1 or off to start being negative 1. So you think of these lights, and now what are the x's and y's? You think that each row, an xi or column, yj, can switch all of its lights. You have a switch for each row and column that will switch all of them, ons to offs and offs to on. Then the claim is that there exists a choice of switching of the rows and the columns, such that n to the 3 halves more lights are on. So if you take the difference of on and off lights, there are more lights, but not only just strictly more, there's actually quite a bit more. There's n to the 3 halves more lights, right? So you should think of it that, of course, you can always just get at least as many on lights is off lights, because you could just take, for example, the rows or just the columns, and if a row has lots of lights off, you would flip it to on, and that guarantees that indeed you will end up with just strictly more lights on than off. But what if you want to get significantly more? And I will point out a nice remark that the existence of Hadamard matrices shows that the end of the 3/2 here cannot be improved. So it is of roughly the right order, therefore. So another nice theorem where what we're proving matches up with what is kind of best known. So how are we going to do this? What randomness should we use? What variable should we track? How will we use expectation? So this one is particularly nice in that it does something a bit different than what we've seen before. How so? Well, the proof idea is don't use all the randomness. So instead, we're going to let the yj's, the columns, be random. So we're going to randomly switch those. And then, depending on the outcome of that, we'll let the xi's be determined later. So once all the columns have done their switches, then and only then will the rows make their decision based on those outcomes. So this is a nice example of using somewhat partial randomness. Do a bit of randomness, and then for the other choices, make deterministic ones, make deterministic choices, depending on the outcome of the randomness. So this works better because if we just took random for everything, in expectation, you'd have an equal number of on and off lights, and that's not what we want. We want significantly more. So that's what we're going to do. And again, this is somewhat, well, reminiscent of the method of alteration, which we'll discuss next week, where we take a random outcome and alter it. Yes, it's like that, but in some ways it's more this doing partial, that we have only using some of the randomness involved. So let's do this in practice. That's the proof idea. Let's actually do the proof. So we'll let the yj's be chosen independently and uniformly. They're plus or minus 1. And then we think of the row sums. So let Ri denote the row sum. That's the sum over Aij, Yj over the j's, of course. So the columns are randomly activated. Now each row has a row sum of how many more lights on than off. And then what we're going to do is we're going to take R to be the sum of these absolute values. So for each row, we kind of view what's the difference, right? Does it have a lot more on than off or off than on? Let's sum up those differences. And then we note that the Aij, Yj is plus or minus 1 with probability half, regardless of the Aij. So regardless of whether a light is on or off, if we're randomly flipping it, then it's viewed as on or off with equal probability half. And so since that only depends on the column, each row can view each light as a independent uniform plus or minus 1 variable. So Ri would be the sum of n independent uniform plus or minus 1 variables, which is useful because we actually then would know that Ri is approximately the square root of n times capital N, where capital N denotes the standard normal distribution. So as in doing random walks, Gaussian distributions here, so we know that it's roughly that. And then therefore, what can we actually say? We know what the expectation of the absolute value of Ri is. Using calculus, you can derive that it's square root of 2 over pi plus little of 1 square root of n. So again, why is that? So if we're just taking the expectation of the non-absolute value of just Ri, of course it's 0. You'd expect equal number of on and off lights. But if we're asking what about the difference between this absolute difference, then that actually tends to be more about square root of n. You should be able to somewhat remember this from the Gaussian distribution, square root of n here being, when we renormalized it, its standard deviation. So most of the Gaussian lives within a standard deviation or two, but indeed a lot actually does. So you would expect that distance to be roughly on the order of the standard deviation of square root of n. So that's what we're going to use, and now we can use our linearity of expectation. So by the linearity of expectation, E of R, since R is the sum of these absolute values Ri, would be the sum of the expectations. So I equal 1 to n of the expectation of the absolute value of Ri. Since that, as calculated above, was root 2 over pi times square root of n, it's the same for each. So there are n terms, so we get square root of 2 over pi plus little o 1 times n to the 3/2. So that's where that number from the theorem comes in. And now we're almost done, right? So we have all these row differences in absolute value, and we know that there is therefore a choice of yj's, a choice of the randomness, with big R, at least the expectation of R, which is the number above. Now, why are we almost done? So we use the randomness, tells us that it's actually kind of likely, there's this expectation that there's a lot of difference in each row of lights on and off. And so when we sum up those differences, we can actually get an outcome of the randomness where there are a lot of differences. The issue is that each row might have more lights on than off, or more lights off than on. So there might be somewhat the wrong direction. But this is where we can use the rows themselves to adjust. So the idea is that we then choose xi with the same sign as ri after we've made this choice of the yj's. So what do I mean is, if a row has more lights on than off, we keep it, we don't switch. If it has more lights off than on, we do the switching. We switch those to on. So therefore the differences, even if they're negative, will go in our favor. And we'll end up with this number of more lights on than off. So this is where we nicely use this deterministic. So we're making the xi deterministic based on this outcome of the ri's based on the yj's. And now we're almost done. We can just conclude that the sum that we're interested in, this aij xi yj, of course that's equal to the sum of xi times the row sums ri. Since we picked xi to be the same sign, we actually get that this is the sum of the absolute values of the ri's, right? Since if ri is positive, we keep it positive. If it's negative, we flip it. And in this way, we get that the sum is actually equal to r by the definition of r. And we knew by the choice of y's that that was at least the square root of 2 over pi plus little o1 times n to the 3/2, which was its expectation. And thus, we conclude the proof. So this is quite a nice proof in that it's nice that we can unbalance the lights, and an amusing interpretation there, but also in how we use the randomness as an example. That we did one random choice and then based on it did a deterministic finish to get the outcome that we wanted. So that concludes our examples for today, where we covered the Hamiltonian paths, large bipartite subgraphs, balancing vectors, and unbalancing lights. Lots of examples of linearity of expectation. So until next time, see you then!